All right, we are going to be looking at simple harmonic motion specifically for the torsion pendulum. Okay. Our goal here is we want to create an equation that has the form of alpha is equal to negative omega squared theta, where omega here is the angular frequency, alpha is the angular acceleration, and theta is the angular displacement. Now, if you don't know why we want to get this form, go down in the description. There is a link to how to set up a simple harmonic motion problem in general. All right, so here we go. We are going to try and get into this format. So what we're going to do is we're going to start with the sum of the torques is equal to I alpha. Okay, that's where we're going to start. We're going to start with that Newton's second law and the rotation. Now, if you haven't seen a torsion pendulum before and you're not sure what that means, a torsion pendulum, you can imagine I have a string, and I'm going to go ahead, maybe here would be an example. If I twist this stopper down at the bottom and I twist it enough, it's going to rotate back and forth. Okay? And so that's what a torsion pendulum is. So it's typically there'll be a disc mounted on a wire, or even it could be something a little more sturdy, like a rod could be here. And it's going to twist that rod, and then that rod is going to spring back and forth. And so it has a very similar setup to that of Hooke's law. It's just more in a rotational sense. So we have the torque produced by our wire or our rod is equal to negative the torsion constant, which we use beta here, times the angular displacement. And the negative is just telling me that the displacement and the torque have opposite directions. Okay? So if we are twisting it this way, the reverse torque is going to be produced back the other direction. Okay? All right. So this is my only torque acting on my disc. There's no other forces here. So we're going to go ahead and plug that in. So negative beta times theta is equal to I alpha. Now I want to just get into this format here. So I have the negative, but I have this I next to my alpha. So I want to move that over here. And so I have alpha is equal to negative beta over I times theta. And so it's that beta over I. You'll notice, look for that mirror here. You'll notice beta over I is where the omega squared is. So what I can conclude then is I can conclude that omega squared is equal to beta over I. So the angular frequency is dependent on two things. What is the torsion constant? And what is the moment of inertia of the object that is being twisted? Okay. And so from this point here, we can go ahead and find omega and just say it's the square root of beta over I, whatever those variables are. In many cases, we do go ahead and we find the period as well. And so the period is going to be 2 pi divided by omega, our angular frequency. And so then we go ahead and we get the period to come out to, and this 2 pi is just getting us into a radians situation, by the way. I end up with 2 pi times the square root of I over beta for the period. Okay. So let's go ahead and see how this gets used. So the example I have here is I have a disc with a mass of 0.8 kilograms. It has a diameter of 0.2 meters. And I notice that when I put it on this wire, it goes ahead and it has a period of 3 seconds. So it takes its sweet time, but it still has a period of 3 seconds. I want to go ahead and find that torsion constant for my wire. Okay. So I was given period. I'm trying to find that torsion constant. I do have to kind of go ahead and figure out what I is. So this is a disc, it tells me. So for a disc, the moment of inertia for a disc is going to be 1/2 mr squared. Notice this is an r and that's a diameter, so I do have to account for that. And then I just need to solve for beta here. So I have period divided by 2 pi squared, and then is equal to I over beta. So now I just need to solve for beta. So beta is going to equal 4 pi squared I, which is 1/2 mr squared, all divided by the period squared. Okay. So I divided that whole term over there. I moved the stuff in the denominator of the denominator up to the top. If I plug in my values here, and notice I do have to convert this, so the radius is 0.1 meters. I find out I get a torsion constant of 0.017. Now, the question is, what units do we have on this torsion constant in this situation? And so you end up with Newton meters, the torque, per radian. Okay. You could have it in per degree as well, but we are going to be using per radian. The reason for that is once we go ahead and we get into doing these, we're going to be wanting it in radians. We don't want to have that degrees out in there, okay? Because we're going to want our thetas in radians, okay? All right, that's it.